we know that Huffman coding is optimal, but unfortunately Huffman does not scale up in the sense that if you want to get close to the entropy with Huffman, then you're going to have to use blocks. So if this is our sequence of source symbols, then you would group these guys into blocks. And then you would have a code word for each block. And to get close to the entropy with Huffman, in general, you have to be taking arbitrarily large blocks. But the problem is that the number of possible blocks is growing exponentially with the block size. So your computational complexity is growing exponentially with Huffman. So this is not at all a practical approach toward getting close to the entropy. On the other hand, arithmetic coding does scale up. So you can think of arithmetic coding as sort of having, by analogy here, having arbitrarily large block sizes in some sense. You're encoding the whole file as sort of one big block. And fortunately, you can do so in a computationally fast way with arithmetic coding. And further, as we're going to see in this video, you can get very close to the entropy of a very natural IID model of the source. In fact, with the infinite precision version of the algorithm, which is completely impractical, of course, but analytically useful, with the infinite precision version of the algorithm, you can get within 2 bits of the entropy on average, and that's within 2 bits for the whole file. So on average, you're getting within 2 bits of the ideal encoded length. And that's for the whole file. It's not just, not just per symbol or per block or something. That's within 2 bits for the whole thing. So this is really a quite remarkable property of arithmetic coding, that not only does it scale up, but it still is very near to optimal. Now, of course, the infinite precision version of the algorithm is impractical, but it turns out that the finite precision version of the algorithm still gets pretty darn close to the entropy. Empirically, the finite precision version still gets within a few bits of the entropy. So let's go through the analysis of this near optimality, of this how does this arithmetic coding procedure get you within a couple bits. So the setup, to set things up here, we have our source alphabet as usual, and we're going to take this to be 0, 1, 2, 3 up to n. And our end of file symbol, as usual, is going to be 0. And we're going to have some probability mass function. We're given some p on this source alphabet. And so when we're doing the encoding, we're given some sequence to be encoded. So we could write over here. So we're given some x1, x2, and so forth up to xk, and then it's terminated by a 0. And each of these xi's is in our source alphabet, and it's not the end of file symbol. So this is some valid sequence with respect to our end of file symbol convention. So let's write down what this set is. So this set, let's define this thing. Let's write down, so this is, let's call it x star circle. It's not exactly x star, so we have to give it a slightly different name. So it's this set of these finite length strings that are valid with respect to our end of file symbol convention. So it's x1 up to xk, and then 0, xi is a non-zero symbol, and k is some non-negative integer. So this is all of these finite length strings. So now, a natural probabilistic model that we can define on this set, a natural PMF using this p, is the following. So we could define the following. P star circle, write that a little more clearly, P star circle on this set, so it's taking one of these sorts of strings, and give it a probability px1 times px2 up to pxk times p0. So this is a very natural IID sort of model on this set obtained using this p on the individual symbols. Now, it may be, look very natural to you since it's the product of this sequence is the product of the probabilities. This is IID. But since this is uh, an infinite set where the sequences are actually variable length, then it's not immediately clear, perhaps, that this is in fact a probability mass function. In other words, that it sums to 1. So here's one way to see that it is in fact a PMF, and that's by observing that there's a certain generative model that generates strings, these kinds of strings, and the probability of generating a given one is this probability right here. And so here's that argument. So say we had x1, x2, let me scoot that over a little bit more. Say we let x1, x2, and so on be some infinite sequence of random variables drawn IID from this P right here. So let this be true. They're independent and identically distributed. And then consider the sequence that we would get by concatenating these guys together. x1, x2, xk, up until we get the first 0, and then we stop, and we throw all the rest of them out. So this k here, the last k, the last xk before we get a 0, is going to be a random quantity. This k is a random variable. That's why I wrote it as a capital K. So this capital K is going to have the property, it's a random variable such that k plus 1 is the first 0. So k plus 1 is the smallest integer I such that xi is our end of file symbol. And then we stop. But this is a random variable. Now, what is the probability under this generative model that I just described of getting a given sequence x1 up to xk and 0? Well, it's the probability of that capital X1 equals little x1 and capital X2 equals little x2 and so forth up to capital XK equals this x capital K, and then the xk plus 1 is a 0. And since these are IID random variables, then the product of that, or the probability of that event is the product of the probabilities, and the probability that x1 equals little x1 is exactly p of little x1, right? Because it's drawn according to this distribution p. So we see that the probability of that happening is exactly this right here. It's exactly just the product of these probabilities. And since this procedure is that this generative process generates samples in which each sample has this corresponding probability, and it's guaranteed to stop with probability 1 as long as p0 is positive, then in fact this must be a probability mass function. So that's one argument for how you could see that this is a PMF. Another way would just be to directly sum this up, sum over all the possible elements in this set, and you could do it that way also, and you would get the same result. So you would get that, of course, well, that may not be obvious to you, but you would get the same result, that the probability under this, I'll abbreviate a sequence of this form by just x. If you sum up over all of those possible sequences, you get 1. Now, one other thing to note about this is that this random variable k has a geometric distribution. So this is another way that you can interpret this model, is that k is geometric with parameter, let's see, so the probability of getting a 0 is p0 at any given step. So this is geometric with parameter p0, and there's a couple different versions of geometric random variables. This one is the one where it can be 0. So if you had a sequence of coin flips where the probability of getting tails or getting 0 is p0, then this would be the number of heads that you got in a row before getting your first tail. So it could be 0. The first one could be a tail with probability p0. So it's probably straightforward, if you know what a geometric random variable is, for you to see that in fact that this k is geometric. And another way of interpreting this model is that you could draw k geometric and then draw x1 up to x capital K IID from P conditioned on the fact that they are non-zero. So there's this conditional probability of P given that it's not zero, and so you could draw K and then draw these from that conditional probability, and you would get the same thing. So that's just another way of interpreting this probabilistic model right here. Now, that actually points out something which is maybe not so desirable about this particular model, which is that in effect we're modeling the length of the messages to encode by a geometric distribution. And that may not be a very good choice of distribution. Of course, it depends on the actual distribution of what you're trying to encode. And but this is a very natural model to take. Very natural model to take of a it's sort of a variable length IID model. You could think of it maybe sort of in that way. Now, arithmetic coding is certainly not tied to this exact model, although the analysis that we'll do in this video will use this model since it's very simple. Arithmetic coding actually can be applied to very general probabilistic models, and we'll talk about how that works later on. And so you can actually, with a very general probabilistic model, still get very close to the entropy. And the analysis is essentially the same. So for the moment, let's focus on this model. All right. Now, we're interested in finding how good of compression we get. So the way that we will quantify that, or the natural way to quantify it, is on average, what is our expected encoded length? So let's call that L star circle. So if L star circle is the expected encoded length, this would be like the sum. It's just the expectation of, if we denote the encoded length of a given x, so I'm using x here for this input sequence to be encoded, it's the encoded length, L of x, times the probability of having that message to encode, and this is the sum over all of these possible messages. That's just the expectation of the encoded length. So we know what this P star circle is, but what is L of x? Let's get a nice expression for this length right here. So L of x, well, it's the length of the encoded message, and what's that? That's just the number of bits that we need, number of bits to encode for the interval from A to B for some, the interval corresponding to whatever our given sequence is, which we're denoting by x here. But this is x right here. Or in other words, so since we're choosing the smallest possible binary sequence, this is the min, this is the smallest, I'll call it m, the smallest integer m, for which the interval corresponding to, smallest m for which there exists some binary sequence. So there exists beta 1 up to beta m binary such that the interval corresponding to this sequence, beta 1 beta m, beta 1 up to beta m plus 1 over 2 to the m, that this interval is contained in the interval from A to B. That was exactly what we were doing in the encoding process. We were doing those binary splits until we found some binary interval that was contained in the interval from A to B. So let's visualize. So maybe we'll go back up to our example and visualize this. So we have this interval from A to B. Maybe I'll draw it over here. This is A, this is B. And so let's remind ourselves of what was going on, so we can figure out what this m is, what this L of x is for a given x. So back up here, let's go back. Yeah, let's use this. So this is our example 2 here. So we had our interval from a to b, and then we were subdividing the interval in these binary splits and dividing until we got down to a tiny little binary interval that was completely contained. So we got way down to this small, this little, the binary interval corresponding to this sequence right here. The interval corresponding to this guy was completely contained in the interval from a to b. And so what you could think about this as doing is sort of taking this interval and, dividing it in half, and then dividing each of those halves in half, and then dividing each of those in half again. So you have, eighths, and then, so you have halves, and then quarters, eighths, sixteenths, and so on. And you just keep doing this. Another way to think about this is just keep doing this until one of those little bits, one of those little, not bits, but one of those little chunks is completely contained in a to b. So let me draw that down here just for our visualization, so we could visualize that process. It's just this type of thing, and we just keep going until we get something that's completely contained in a to b. And so a to b, a to b would be like some, wherever it was, something like this. And so how many times, so m here, this m, or not m, but L of x, the smallest such m, is going to be the one for which, maybe I'll put this here. It's going to be, it's just what I said. So so it's the first m for which one of these intervals is completely contained in here. So it wouldn't. So in this example here, as I've drawn it, it wouldn't be 1. It wouldn't be 2. It wouldn't be 3, because none of those is contained. But then it would be 4. So 4 would get us one that was then this guy right here. This would be completely contained. So it would be 4 in this case. And in general, we can upper bound L of x in the following way. So the width of these intervals at the mth step is 1 over 2 to the m, right? After the first step, the width is 1/2, and after the second step, the width is 1/4, and so forth. And so at the fourth step here, they were like 1 over 16. And as long as the width of these intervals is less or equal to half of the width of the interval from a to b, then we're guaranteed that one of them will fall in this interval, right? Because, say it were exactly half, then the worst case would be kind of, if 1 over 2 to the m, as long as this is less than half of this distance, b minus a. So if it were exactly half, then sort of the worst case would be that, it split the difference right down the middle. And then this one, right? So actually both of these intervals here would still be contained. But it could happen that if you were a little bit bigger, like here, then that would be sort of the worst case, and neither of them would be contained. So we are guaranteed, if you think about that for just a minute, you'll see that as long as 1 over 2 to the m is less or equal to half the distance from a to b, then we're guaranteed that m satisfies this condition. There exists some, as long as we're less or equal to half, then there exists one of these intervals that's contained in a to b, and therefore L of x must be less or equal to m, because it's the min of all those m's. Now, so we have this. So this is nice. This is a nice characterization of this length. We have this nice upper bound under these conditions. So let's play around with this a little bit. So how can we rewrite this? So this is true if and only, move the 2 over, move the, so we could rewrite, well, it's just a simple way to rewrite this. We just move the 2 over. This is true if and only if 1 over 2 to the m minus 1 is less or equal to b minus a. And so what is this b minus a? Now we seem to need this quantity. So let's see if we can figure out, get an expression for this b minus a. So b minus a was the width of this interval here. And what is that? Well, in this case, it was p2, p3, p2, p0 in this example. And, oh, and right, remember that we noted that the length of this interval, b minus a, is always going to be the product of the probabilities in the sequence that we were encoding, px1 up to pxk times p0. So this is always true, that we always have b minus a is equal to this. So, and that is exactly what we defined our p star to be. So that is exactly the probability of that sequence under this model. So that is the key fact. The fact that the length of that interval from A to B is the probability under our model of the message to be encoded. That is what is going to give us this good performance. So we could write here, instead of b minus a, that's just the same as p star of x. X is this sequence right here. It's because this is, remember, p star is just, this is the product of those probabilities by definition. So how can we rewrite this? Well, let's move the 2 to the m minus 1 over, move the p over, and take logs. So if we do that, what do we get? We get that the log, let's do the base 2 log, 1 over p star of x is less or equal to, log is order preserving, less or equal to m minus 1. All right, so this is starting to look pretty good. Let me clean this up a little bit. So this was sort of the key step right here, and this was because p star circle x equal to that is always equal to b minus a. So we have these implications here. These implications hold for any integer m. You know, as you can pick any m you like, and these implications hold. So let's choose a particular m. So let's choose the following. Let's choose m. So choose m to be equal to, we can just pick any old m we like, and we'll have these implications. So let's choose this particular value of m. It needs to be an integer. It does need to be an integer. But let's choose it to be this thing here, log base 2 1 over p, rounded up to the nearest integer, plus 1. Well, what do we have then? That implies that log, well, of course, so this implies, of course, that log base 2 1 over p is less or equal to this, and that's, so this implies log base 2 1 over p star x is, that is certainly less or equal to the same thing rounded up, and that thing rounded up is just m minus 1. Move the 1 over. So we know that if we choose this m, that we have this condition, and that is exactly this condition right here. So if we chose this value of m, we have this implication, we have this implication. These are exactly the same thing. We have this implication, this one, and then this one. And so we know that for this value of m, this holds. And we conclude all of this together implies that L of x, you do a different color, L of x, all of this, implies that L of x is less or equal to this particular value of m, which is log base 2 1 over p star x, p star x, let me write that clearly, rounded up, plus 1. So we have, so this is a nice result here. This gives us a nice upper bound on the lengths. So that's a good sign to have an upper bound, because we would like to say that the lengths are small on average. The encoded lengths are small. Now, what can we say about this? So there's we can take a little shortcut here. We could actually just use this to directly analyze the expected length. Remember, so we now have this bound, and we're going to use that in this expression right here. But we can make an observation that this right here, without the +1, is exactly the lengths of a Shannon code for this probability mass function on that set, right? So before we were only thinking about Shannon codes in the context of encoding like one symbol at a time or blocks at a time, but you could just as well define a Shannon code. In principle, you could define a Shannon code on this whole big set of all of these finite length sequences here that satisfy our inner file condition. So you could define, in principle, a Shannon code. Oops, what happened? Boom, there it is. You could define a Shannon code on that set, and its lengths would be these by definition, by construction. And we know that the Shannon code always has the following property, that its expected length, so I'll put LSH for the expected length. This is now going to be the expected length of the entire encoded file, since in this setup, our source symbols are the entire message to be encoded. These are our source symbols. Each entire message is its own source symbol. So the expected length of the whole thing, the whole encoded length, is strictly less than the entropy plus 1. And here it's the entropy now of this distribution. This is our distribution on our alphabet. And of course, we always have that it's greater or equal to the entropy, right? And so now, what do we know about our L star? This guy right here. Well, we know that these lengths, these lengths, I'll put maybe LSH. So this is lesser. So what is this? L, we have our bound. L of x is less or equal to this. And this is, so I'll just write it here. This right here, I'll call this LSH of x for the lengths of the Shannon code. The Shannon encoded they're sort of code words, but there's a code word for every possible source message. So this is LSH x plus 1. So the L star, let's see, where should I put this? I'll just write it here. So L star, so I don't have to keep going back up to there. I'll just write it here. This was the sum over lengths, P star x over all x in x star circle. And so we have that this is less or equal to the Shannon lengths plus 1. And so this is just LSH plus 1, because you multiply the P star of x times 1, and when you sum that over all of them, you just get 1. And then the other part, you're left with the Shannon expected code word length, expected encoded length. So we can conclude, since LSH is less than, this is less than the entropy plus 1, plus this is less than the entropy plus 1, and then we have to add another 1 for this guy. So we can conclude that the expected encoded length, so here is our nice result. The expected encoded length, and I'll put the lower bound too. So the expected encoded length under arithmetic coding is less than the entropy of this model plus 2. So it's within 2 bits of the ideal, because this is also for any uniquely decodable code. Whoops, not H star, H2. This is lower bounded by the entropy. So we're within 2 bits of the optimal for the entire encoded message. I think that's pretty cool. So that's worth writing down. So within, i.e., within 2 bits of ideal of the entropy for the whole, for the entire message. So in other words, on average, if you're encoding files or if you're compressing files, then the compressed size of the whole file is going to be within 2 bits of the ideal compressed length. Within 2 bits of the best possible compressed length under this probabilistic model. So of course we're assuming that so this is on average that you're within 2 bits, and it's assuming that the true things that you're compressing are coming from this distribution. And of course, in general, that may not be the case, so you need to choose an appropriate distribution if this one happens to not be appropriate. And we'll talk about later how you do that. And in fact, the arithmetic coding procedure is it's basically the same with some minor modifications to handle pretty arbitrary models, probabilistic models, and you can get a very similar result. All right, so this is a very nice result, a very nice property of arithmetic coding. And so one question that you may have at this point, since we were using the Shannon code here, you may be wondering, well, hey, why not just use the Shannon code? The Shannon code is within 1 of the ideal, right? And in principle, you could use the Shannon code, but what's not clear is how you would actually computationally implement this in a way that is that gives you reasonable computational performance in terms of how long it takes to actually implement this. Because the usual thing we did with Shannon code was we had a we explicitly constructed the code, but now you have like these infinitely many things, and it's not really clear how you would actually go about doing that. So in principle you could, but in practice it's not clear how you would implement it. In fact, if you tried, if you were to go about trying to sort of figure out how to do that, what you would end up with is probably basically arithmetic coding. All right, so this is the near optimality property of arithmetic coding.